Okay, welcome back. So 9.4, there, 10 here. Comparison tests. So it's a little like the integral test, theoretical wise. You have a series, you know the behavior of it. Before in the integral test, you have an integral that you know converges or diverges. And you can compare it to another series that you don't know if it converges or diverges, and you can make a conclusion based off what you know about the one series that is kind of similar to the other series. Okay, you may already kind of feel this way. You'll see in a series like 1 all over n plus 1 from n equals 1 to infinity versus the series of 1 all over n from n equals 1 to infinity. These guys are pretty freaking similar. I mean, this is just the harmonic series missing one of the terms, basically. It's missing one. Anyways, they're both going to diverge. Okay? And generally, you don't want to make that kind of assumption. You don't want to make these grand statements like, "Whoa, I think this series 1 all over square root of n sine of n looks a lot like this series 1 all over sine n. So therefore, if this converges, this converges. It's a little more technical than just that. And obviously, in this case, yeah, it is just that. But in general, you have to go by these comparison tests. Okay, so there'll be some criteria you have to make sure are in effect, and then you can make your conclusions. Okay. Okay, so the first kind is the direct comparison test. And I just do a couple of warm-ups because what you're going to be doing is comparing the terms of two series and seeing if one is bigger than the other for all n. And this is something that we generally don't do very much. It's the actual way you would do this if you were a little more into math is probably a direct proof of some sort. Some people may say, "Ooh, I got to do an inductive proof," but I think it's really a direct proof scenario. Anyways, we're looking at terms of series. So when I say terms of series, I don't mean the whole thing. I just mean this thing. Okay, that's what I'm looking at, and I'm comparing the terms of this series to the terms of a series I know. Okay, and generally I can go from here to here by just kind of lopping off a bit of the terms. So I want to make a comparison, an inequality. Is this less than or equal to this, or is this greater or equal to this? Well, I've increased the denominator going from here to here, therefore I have decreased this expression, so it must be that this is greater than this. And then usually you want to make a statement about the n values, because sometimes you may have to go out to n equals 5 to make sure it holds. Please note that what I'm not doing is just checking one or two values. I'm not plugging in n values and saying, well, this number is less than this number, therefore it's always going to be the fact that this is greater than this, or whatever. It doesn't work like that. You're not looking at a particular case. So the example I always tell my students is if you drive to work on 100 miles per hour and you don't get caught, does that mean you're never going to get caught? And the truth is no. You want to be a little bit more careful, right? Anyways, here's number 6. 4 to the n all over 5 to the n plus 3. And then I'm comparing that to 4 to the n all over 5 to the n, which is the same as 4/5 to the n. So in this case, I've decreased the denominator, therefore I've increased this expression. Number 7, ln of n all over n plus 1. Whoops, I forgot to say n is greater than or equal to 1. Comparing this to ln of n, we could do even better than that. Well, no, let's just do ln of n all over n. So in this case, I've decreased the denominator, therefore I've increased this expression. If n is 1, you have equality. So you actually have to go and say, let n be greater than or equal to 2. Number 9, here's a good fact for us to know. the n factorial grows fast as cussing. It is out of control. This guy will outproduce this guy any day of the week. And in general, n factorial will outperform any base to a power. Okay, so you put it like 100 to n factorial will get bigger than that eventually. Right. So this denominator will be eventually bigger than this denominator. Therefore, this should be smaller after a while. And we'll say this is going to happen for n greater than, I think it was maybe 3 will be where it starts to work. If you have 1, obviously 1 is not less than 1/2. So you have to make sure you go out a little bit. The book probably mentions the limit as n goes to infinity of k to the n all over n factorial. This thing is equal to 0, and that just again points to the fact that the n factorial grows much, much faster than k to the n. Okay. So it's a nice fact to know and have in your back pocket. Okay, so anyways, what is then the direct comparison test? Let's take a look. Theorem 9.12, the direct comparison test. So we'll let 0 be less than a sub n, less than or equal to b sub n for all n. And then one of two things will happen. First, if the series b sub n converges, it'll force the series below it to converge. Then secondly, if this guy diverges, it forces that guy to diverge. Okay, I just want to take a look at the proof of the second one really quick. Sorry, I guess it's the first one I want to look at. Yeah, sorry, the first one. Okay, so suppose then the sum of these Bn terms converge. Right? So we can call that something, right? We can say, so the sum of B sub n equals L. Because we have this inequality holding, because the A sub n terms are less than or equal to B sub n for all n, we must have this sequence of partial sums being bounded above. Okay, so the sequence of partial sums from the A sub n series. Okay, so S sub 1 would be A sub 1. And of course, that'll be less than or equal to B sub 1, which is obviously less than or maybe even equal to this series B sub n. And of course, we know B sub n equals L. Then S sub 2 is A sub 1 plus A sub 2, which is less than or equal to B sub 1 plus B sub 2, which is less than or equal to the series B sub n, which of course again is equal to L, etc. Right? We have a sequence which is bounded above, and then on top of that, the sequence is increasing. Okay, so what does that mean to us? Well, if you remember from 9.1, we had the monotonic bounded theorem, which said if that's the case, then the thing is convergent. So hence, the limit of S sub n is equal to something. In particular, what was S sub n? Well, S sub n is just the sum from I equals 1 to n of a sub I. And of course, that's just the sum from I equals 1 to infinity of a sub I. In other words, this thing is convergent, which basically means it adds up to something. Okay, so the other statement just follows from one. It's the logical contrapositive. So if A, then B, that implies if not B, then not A. Okay, so you want to be a little careful. You don't want to commit what's called converse rules, or a converse error, where you go if A, then B implies if B, then A. That's not true, right? Not necessarily true. You can do a contrapositive move, and that's what's been done here to get the other point of fact. Okay, so anyways, in practice here, the way I want you to use the test is as follows. I want you to show A sub n is less than or equal to B sub n for some n. And secondly, state the known convergence or divergence of the known series. Okay, so in the beginning, you don't really know which one you're dealing with. You don't know if you have a B of n or A sub n. You kind of have to experiment to force a conclusion. Okay? Thirdly, then, you make your conclusion. Okay, so I should see 3 steps when you do these problems. Okie dokie, so here's number 3. We have the sum of 1 all over 2n minus 1 from n equals 1 to infinity. Okay, so first I want to do a comparison, hopefully with a known series. And I'm comparing terms, not the entire thing, just the terms of the series. So 1 all over 2n minus 1, comparing that to 1 all over 2n. Okay, okay, so if I increase the denominator, I have decreased this expression, so the inequality will be in that direction. This will hold for n greater than 1. Okay. Secondly, then I make a statement about this thing right here. It should be a known series, and for us to have a conclusion, it has to be divergent. If it's convergent, it won't give us any conclusion. Okay, so we hope it's divergent. If it's not divergent, if it's convergent, you have to try a different series. Okay, so the series 1 all over 2n, it is basically a constant times a harmonic series. And the harmonic series is divergent, so therefore this series is convergent. Okay, so in this case, we can conclude, because this guy is less than this guy, that this guy diverges. Like this guy is getting really, really big, and it's kind of forcing this guy to get really, really big. Okay? So in the end, we can conclude the given series diverges. Okay? Okay, so compare that example to this example, which seems like the same deal, right? N equals 1 to infinity of 1 all over 2n plus 1. Instead of minus 1, I just went plus 1. And you'd think you could do the same thing, right? So first, you compare 2n plus 1 to 1 all over 2n. And the problem is that this thing is actually going to be greater than this thing because I've reduced the denominator to get there. So you don't have the forcing happening. You know, this is divergent, but that doesn't tell you anything about something that's less than it. Okay? So no conclusion can be drawn in that case. So what do? Well, you try again. So instead of decreasing the denominator, I got to figure out a way to increase it, right? So 1 all over 2n plus 1. And you can increase it cleverly by just replacing 1 with an n, right? So n will be greater than 1 for all n greater than 1. And this expression will be 1 all over 3n's, which is then going to be less than this expression here. Right? And then this guy is just a constant multiple of the divergent harmonic. And therefore, it's also divergent. Okay, so my conclusion is that the original series diverges. Alrighty then. I guess we got one more. It's number 5. We have a series from n equals 2 to infinity of 1 all over the square root of n minus 1. So first, 1 all over square root of n minus 1, compare that to 1 over square root n. There's a series of 1 over square root of n is a p-series, right? That's equal to 1 all over n to the 1/2. And that's divergent. Okay, so we kind of need this guy to hopefully be less than this guy. If it's greater than, we're screwed. We got to do something else. Okay, so going from here to here, I've increased the denominator. Therefore, yeah, that's definitely less than. And I can conclude that the original series diverges. Okay. All right then. The other test is a little bit easier on the stomach. It's the limit comparison test. So what does this say? It says suppose a sub n is greater than 0 and b sub n is greater than 0, and the limit of a sub n all over b sub n equals L, where L is greater than 0 and finite. Then the two series had the same behavior. Then the series a sub n and the series b sub n have the same behavior. Okay, so again, you're doing a comparison with a known series and having this pan out for you. Now let's take a look at this proof too. Okay. So the proof, we make our supposition. Suppose a sub n is greater than 0 and b sub n is greater than 0. And also we have this limit of a sub n all over b sub n equals L, which is greater than 0 and finite. I think we could just jump to the strict definition of a limit. By the strict definition of the limit, we can kind of bound this ratio away from 0. Because if we know this expression is getting really, really close to some number L, eventually, when we go past some number n, we can ensure that the sequence is inside of whatever epsilon we want. And in that case, we can assure that it's never going to be, it's always going to be away from 0. So it's always going to be greater than 0. Okay? As a matter of fact, we could say that there's probably some sort of lower bound to it and an upper bound to it. So we call this little m and this big M, and say, by the strict definition of a limit, eventually a sub n all over b sub n will be less than m and greater than this little m, which is greater than 0, for n greater than this big N we have over here. Okay? All right, so multiply all three sides by b sub n. So I get 0 less than m times b sub n, which is less than a sub n, which is less than big M times b sub n. And what's happening here is we're setting ourselves up for the direct comparison test. Okay, so we have this holding, and supposing the series b sub n converges, that tells us the series m times b sub n converges. And then if this converges by the direct comparison test, it forces the series of a sub n to converge. Okay. And then you can play the same game in the other way. If the series b sub n diverges, then the series of this term, of these terms, diverges, and it'll force the series of this term to diverge by the direct comparison test as well. Okay. So doing the direct comparison in practice, then, you want to pick a series that you know about to form this limit, and then do the limit and make your conclusion. Okay, so let's look at 13. We have the series of n all over n squared plus 1 from n equals 1 to infinity. The way you pick your series is basically the same way as before. You're just chopping off this unused term. In other words, we're kind of going to look at the series with just n over n squared. So consider the series n equals 1 to infinity of n over n squared, which is the series of 1 over n, which of course is a harmonic divergent, the divergent harmonic series. Right, then we make a limit, which is the ratio of the terms of this series and the terms of this series. Okay, so note the limit. You put this over this or vice versa, it doesn't matter. I'll go 1 all over, no, let's go n all over n squared plus 1 all over 1 over n. This will be the limit of n all over n squared plus 1 times n 1 over, sorry, n over 1. It's the reciprocal of 1 over n. And then this will be the limit of n squared all over n squared plus 1. And then the limit of that is just the limit of n squared over n squared, which is the limit of 1, which of course is 1, which is greater than 0 and finite. Hence, both have the same behavior. This guy was divergent, so it forces that guy to also be divergent. That's the idea. I guess we can leave it like that. One of my students got really concerned with the direct comparison test and basically forced me to write this up for him, one of my Arabic students. So I just wanted to note that. You may want to pause it and take a look at it. This is the direct comparison test. So there's cases where you can't make conclusions if the series you're comparing it with has a certain behavior and you have a certain inequality established. Okay, that's about it. I'll see you next time.